Thank you very much for the invitation, and thanks for the organizers for putting this meeting all together. So I'm going to talk about work based, this talk is based on joint work with Oscar Marmon. And so what I'd like to do actually is not necessarily to talk about a specific problem, but three sets of problems which illustrate the interactions between algebraic concepts. I'll be working with three of them, and also, on the other hand, fractal geometry and metric number theory. So the first problem I'd like to work on is the consideration of the metric Openline conjecture. So I'm going to show that these first two problems, Openline and the problem of approximation on curves, reduce to a third one, which is of a much more algebraic flavor, and then getting ideas from the third one, we'll get back to the first two. Okay? So the Openline conjecture, well, if you consider a homogeneous polynomial of degree 2, a quadratic form, if it is non-degenerate, meaning that after a linear change of variable, you cannot reduce the number of variables to a smaller one. If it is indefinite, meaning that it takes both signs. And if, for obvious reasons, doesn't take discrete values, namely that it's not up to a scaling, well, up to a scaling doesn't have rational coefficients, then it takes arbitrarily small values, provided that the number of variables is at least 3. So actually, Openline conjectured that with at least 5 variables, and Davenport gave the same conjecture for at least 3 variables. And this is optimal because if you consider the case of 2 variables and you consider this quadratic form here, well, by the very definition of what it means to be badly approximable, this form here cannot take arbitrarily small values. Okay? So this conjecture was actually solved by Margulis in '87 using, well, proving a special case of Raghunathan's conjecture for unipotent flows, which was generalized in full generality to Ratner later on. But the main drawback of these proofs is that they are ineffective. So what do we mean by being ineffective? Well, it means that there are at least 2 questions we'd like to answer and we cannot. First of all, what is the size of the smallest solution to our definite inequality? Okay? Second of all, what is the number of solutions to our definite inequality? So as we let the size of our integer solutions tend to infinity. These questions, generally speaking, are extremely hard, and progress has been extremely irregular and very slow. So for instance, if you take the first question, so the size of the smallest solution, well, the best result actually is due, well, just appeared a few weeks ago actually. And it shows that, well, under some suitable definite condition, the size of the smallest solution grows like a polynomial in the inverse of the error term. Okay? So that's really recent. What about the second problem? So the second problem, let me remind you, is about the number of solutions that we want to count. This one is better understood because basically, well, if you consider a quadratic form under suitable solutions, you do get the heuristic that you're looking for, namely that the number of solutions, number of integer solutions, is equal to the volume of the set of real solutions. And in this case, you can explicitly compute what it is in order to show that, well, it's equal to the asymptotic, which is over there. Okay, so that's for the case of quadratic forms, homogeneous polynomials of degree 2. So obviously, what we'd like to do most naturally is, well, can we get the same statement for the case of any homogeneous form? Well, I think that here we shouldn't keep our hopes too high because in full generality, I would say it's hopeless. Okay? So in order to overcome this difficulty, Adiceam and Margulis suggested a metric version of this generalized Openline conjecture. What happens if we indeed consider homogeneous forms, so homogeneous polynomial of any degree, but this time we consider a kind of unimodular distortion of it. So what do we mean? Well, let's take again our first question. So the first question is about the size of the smallest solution. What happens for the size of the smallest solution if we compose F with a unimodular matrix on the right-hand side, and we're looking for the size of the smallest solution for almost all unimodular lattices? Okay? Similarly, if we take the second question, looking for the number of solutions to our definite inequality, what happens in the generic case of almost all unimodular lattices if we compose F on the right-hand side with such a matrix? Okay? And so basically what we should say here is that where does this problem come from? Why did Adiceam and Margulis have the idea of working with a composition by unimodular lattice on the right-hand side? Well, it's a very natural thing to do because what's happening here is that if instead of considering an integer solution, you consider G times an integer solution, it means that instead of working with the canonical lattice, you work with another unimodular lattice. Okay? So in other words, what is going on here is that you're looking for quantitative versions of the generalized Openline conjecture, in the case of any homogeneous form, in the case that you draw your solution not necessarily from the canonical lattice, but from a random unimodular lattice. Okay? You add some randomness by choosing the set of the solutions to be random. Okay, so we're doing some probabilities. So the big question here is, what do we mean by a random lattice? Okay? We need to define a measure. It's a well-studied, so that's the first algebraic concept I'm going to introduce. I'm sure that many of you are extremely familiar with this. Well, it turns out that if you want to write your lattice lambda as g times zn, maybe I should go here, for any unimodular matrices, they both represent the same lattice. Well, it's not dry yet, but anyway. If and only if there exists an integer unimodular lattice such that g times k is equal to h. Okay, so in other words, if you want to write lambda as g times z to the n, well, the g here is only defined in the quotient space which is here. Now, this quotient space is very nice because, well, SLN R can be equipped with a Haar measure, and this Haar measure can be projected down to define, well, a measure on the quotient space. That's the abstract way to define a measure on the space of unimodular lattices. The only thing to keep in mind here is that, well, the measure that we get turns out to be a probability measure. Okay? Now, if you're not familiar with what this Haar measure business looks like and what this measure looks like, basically you can get back to the Lebesgue measure, which we understand much better. And this is due to a beautiful result by Siegel, which tells you that, look, if you take an integrable function f, if you take the sum of the values it takes at all lattice points, if you average against this new measure, then you actually get the Lebesgue measure of your function. Okay, so working with this measure roughly amounts to working with the Lebesgue measure. And let's try and see an example. So for instance, if you take for f the characteristic function of a set A, what you get on the right-hand side is, of course, the Lebesgue measure of the set A. What you get here on the left-hand side is the average number of lattice points falling in your set A. Okay, so in other words, the average number of lattice points falling in your set capital A is equal to its Lebesgue measure. Okay? Well, clearly, the average number of lattice points falling in your set is bounded below by, well, the characteristic function of the event that it should exist at least 1 point. Okay? So if you integrate that, you find this pretty interesting result, well, at least to me. The probability that a random lattice should intersect your set A is bounded above by the Lebesgue measure of this set. Okay? So another natural question you can ask is, what happens is, instead of considering the probability of intersection, you consider the probability of non-intersection. In this case, well, slightly more complicated. You need to work basically with the characteristic function of the complement of A, but there are some technical details to be worked out. And that's Atrea and Margulis who prove that, well, the probability that a random lattice should not intersect your set A is bounded above up to multiplicative constant by the inverse of the measure of A. Okay? Right, so let's keep these results in mind, and let's get back. Oops. I should put this back, I guess. And let's get back to our, well, quantity versions of the Openline conjecture that we're looking for. So again, we're looking in a generic sense for the solution of the smallest solution to our diaphanous inequality, which is written over there. And so the idea here that we're going to do is to apply the Borel-Quantel lemma to say that if a sum converges, then almost always I know that something happens or doesn't happen. So for that, I need to work with discrete variables, and so I'm going to take epsilon to be an inverse power of 2, 1 over 2 to the j. Okay? The value of the minimum, I do not know what it is, so I'm going to call it h. Okay? And in order to implement the heuristic that we had, we're going to work with the set of real solutions to our Diophantine inequalities. So that's the set AJ, which is defined up here. Well, the Borel-Cantley lemma tells you that if the sum of the probabilities of some event, well, converges, then this event cannot happen infinitely often. What does it mean that doesn't happen? Well, if you want this intersection here to be non-empty, it precisely means that the point occurs in the intersection. And if you write this point as being G times M, where G is a matrix defining lambda, it precisely means that there exists an integer vector which is non-zero from the definition of Aj, where you could exclude the value 0, such that the norm of Gm is less than the value of the minimum, and at the same time, you've got the inequality you're looking for. Okay, so less than 2 to the power of minus G. So from the Borel-Cantley lemma, if we know that the sum of the probabilities of this event converges, then we do get precisely that the minimal solution to our inequality is less than H. Well, not quite, because we're looking for the minimum for the norm of M. Here, what we have is the norm of Gm. That's not too much an issue when you work with probability, because you can work with the compact exhaustion of your space. You can work over a subset of your space where the operator norm of G is bounded in such a way that the norm of Gm over this compact subset will be comparable to the norm of M, and you absorb everything in the implicit constant. Okay, so upon doing this little technicality, you do know that if the sum of your probabilities converge, then you're done. But we just saw the Atreya-Margulis result, which tells you that, well, the probability that a random lattice should not intersect a set is bounded above by the inverse of the measure of this set. So to guarantee this condition, it's enough to guarantee that the sum of the inverse of the measures of this guy converges to get precisely the solution we're looking for in a generic sense for almost all matrices. Okay? So if we summarize what is going on here, if we want to look for the solution of the smallest solution, the first thing that we need to do is to compute the sum of the inverses of the measures of these sets. And so as a consequence, the problem at the end of the day amounts to computing the measure, the Lebesgue measure of this semi-algebraic set, which is here. Okay? So I will use this word semi-algebraic pretty often. It just means that the set defined by polynomial inequalities. Okay? And this set in particular, the SFAB, will appear extremely often in our consideration, in our talk, throughout the talk. All right, so again, from the Borel-Cantley lemma, if we're able to compute the measure of this set, then we know we've got a solution for the size of the smallest solution to our definite inequality. We're going to see that computing the measure of this set is exactly also what is needed for the second question that we considered. So the number of solutions to our definite inequalities in a measure theoretical sense. Again, we're going to apply Borel-Cantley. Here, what we really need to make Borel-Cantley work, remember that Ziegel's formula was letting us know that the average number of lattice points falling in a set is equal to the Lebesgue measure of this set. Okay? Well, what we need actually in order to solve this second question is a quantitative version of this estimate with an error term. And the good news for us is that Rogers did so. So Rogers proved that the probability that the number of lattice points falling in a set should depart by a certain quantity from the expected value, which is the Lebesgue measure, again, that's a consequence of Ziegel's lemma, well, is bounded above by an explicit quantity, which depends on the volume of your set and the amount by which you want to depart from the expected value. Okay? And so what we're going to do is to say that, okay, we're going to take, again, for A here, as always, the set of real solutions to our inequalities. And so what we want is that, well, the number of solutions falling in this set should be given by the volume of this set up to an error term. So we will want that the sum of these probability measures should converge so that for large enough values of capital T, we'll get the reverse inequality. Why is it so interesting? Because if we get the reverse inequality, and if we choose the quantity m as negligible with respect to the main term, it will precisely mean that asymptotically, the cardinality we're looking for is equal to the volume of this set. Okay? So again, we'll get the reverse inequality with the error term which is here. And so as a consequence of this, again, Borel-Cantley lemma, we've got that in order to get the heuristic that the number of solutions is equal to the measure of this set, upon adjusting appropriately the error term which is here, we just to make sure that the sum of these probabilities converges, and as a consequence, that the sum of this probability should converge. That's enough for us, right? And so if we summarize all that we did here, we want to count the number of solutions. We need to compute the volume of the set of the real solutions to our inequalities. We need to adjust some parameters in order to make sure that this sum converges. And so at the end of the day, what is left in all these analyses is, again, to be able to compute the volume of this set. So it is exactly the same problem as the one in the first question. So again, if we're able to compute the volume of this semi-algebraic set, then from the Borel-Cantley lemma, we get a quantitative version of the metric, of the generalized metric Openline conjecture. Okay? So again, here's what we did so far is that we want the generalized Openline conjecture. It reduces to a problem of homogeneous form inequalities. And so here is a summary of the goal. We've got, again, the same semi-algebraic set. We want to compute its volume. And we're going to do that in full generality. So in all that I did, actually, B was equal to epsilon and A was any parameter. Let's take the problem in full generality by asking B to be a function of A. So we will only be interested so far in the case where B is equal to epsilon. And so as I said, if we are able to determine the volume of the semi-algebraic set, we do have the generalization of the Oppenheim conjectures that we're looking for. And again, this is a consequence of the Borel-Cantley lemma. Okay? So just one thing, when you look at an inequality like this, where's the rubber? So by homogeneity of the form F, it should be clear that we've got these inequalities here. So F is a homogeneous form of degree D, meaning that if you decompose X in polar coordinate, it's clearly bounded above by the subnorm of F over the sphere times the diff power of, well, the norm of X, again by homogeneity of the homogeneous form F. As a consequence, the above problem here only becomes interesting, and we'll keep this constraint throughout, if the values taken by the homogeneous form are negligible with respect to the diff power of the norm. So this thing is something that we shall always assume to avoid the trivial case, which is just given by this inequality. So we'll always assume that Bt is negligible with respect to t to the d. Okay, so what we need now is to compute a volume of semi-algebraic sets. And in fact, when preparing this talk, I wasn't expecting that there should be so many semi-algebraic sets on the sides of the rooms. So they're all beautiful, a diabolo, a ding-dong, whatever else over there. And so the beauty of these semi-algebraic sets is that we always think of them as being nice objects, and sometimes they are. So here is a lovely, really semi-algebraic set that you like to work with, I guess. A heart. You can check that the equation precisely gives you this. But it can also be extremely ugly, actually. So on the right-hand side, I didn't even bother to write the actual equation of these kind of quantities. But this is the generality of the situations that we need to deal with in order to find the volume of objects like that. They can be either very nice or extremely complicated. Okay? And so again, if we're able to compute the volume of these sets, well, then we will be able to solve the metric Oppenheim conjecture. And so the question is, what is the volume of these sets? And so here is the second algebraic tool that I would like to introduce, the so-called Sato-Bernstein theory. Okay? So what is it about? You consider a homogeneous form F in n variables. To this homogeneous form F, you can associate what is called, and I will define, of course, what it is, a univariate polynomial, depending only on a single variable, which is called the Sato-Bernstein polynomial. Okay? So this polynomial has the property that is monic, it has rational coefficients, but in fact it's even more. All its roots are rational, and they are all negative. And that's the reason why I wrote it B minus S, just to make all the roots positive. Okay, so to a homogeneous form, you can associate a unique univariate polynomial with rational coefficients called the Sato-Bernstein polynomial. This polynomial has this property that it admits a root, so B minus S, which is rational, with values between 0 and n over d. Second piece of information that we need to keep in mind. For all purposes in this talk, you should think of this Rf as being the smallest positive root of B minus S. That's going to be by far the generic case. There are some degenerate cases that we understand pretty well where it can be one other root, another root in 0 n over d, but in the most generic case, you should really think of Rf as being the smallest root of B minus S in the interval 0 n minus d. And so it has a corresponding multiplicity. Well, if you know this root and this multiplicity, you precisely get the volume estimate that we're looking for. Okay? So you get an explicit closed formula. In fact, you can even get an error term if you work a bit harder. But we are able to solve exactly the problem that we're looking for, computing the volume of a semi-algebraic set. And here is a remark which I find pretty interesting. So for instance, when is it true that the volume determined by the inequality f less than a constant should be finite? Well, if you want 1 here, you're going to take b to be equal to 1, so b to be equal to 1. And when b is equal to 1, this quantity here remains constant as the norm of t tends to infinity, if and only if n minus d times r is equal to 0, meaning r is equal to n over d, and when m is equal to 1. In other words, in the generic case, the volume of your semi-algebraic domain is finite if and only if the smallest root of b minus s is equal to extremal value n over d with multiplicity equal to 1. Okay, so that's the kind of information that you can get from the knowledge of the Sato-Bernstein polynomial of this homogeneous form. So of course the question is, what is the Sato-Bernstein polynomial? So it's very appropriate to give this talk now because, as you can see, so it's due to Sato and Bernstein, of course, and Sato passed away just in January this year, I think 2023. And so the Sato-Bernstein polynomial turns out, I'm sure there are people, there may be people who know much better than me in this topic. It's extremely useful actually in quantum field theory to ensure the stability of a number of systems. And so what is it? It's not as scary as it looks like. You take your homogeneous form in n variables, x1, x2, up to x. To this homogeneous form, you can associate a polynomial in a single variable, capital B of x. Let's call it this way. To this one variable polynomial, you can associate what is called a differential operator. So what is it? A differential operator is just a polynomial in the set of variables which are available, x1, x2, up to xn, in an additional variable s, and in the set of partial derivatives with respect to x1, x2, xn. And because of the rules of differentiation, this polynomial cannot be commutative, you denote it with this bracket notation. So it's just a non-commutative polynomial in a formal polynomial in the set of variables which is given up there. Okay? So you can associate a differential operator which satisfies this property that we need to understand the relevance of. B multiplied by f to the s is equal to the differential operator applied to f to the power of s plus 1. Okay? So that's what Bernstein and Sato independently actually discovered. The question was actually asked by Bernstein at the ICM in 56, and Sato proved the existence of this thing. Bernstein also found a different proof. Now, it is clear that the set of polynomials B for which exists such a differential operator is stable by multiplication. Because if you multiply by another polynomial B tilde of S, this differential operator is allowed to depend on S, so the B tilde can be absorbed in this differential operator. Okay? So in other words, the set of polynomials B for which there exists a differential operator is stable by multiplication. This is what is called an ideal in the ring of polynomials. Now, if you do some basic algebra, you know that all the ideals of the ring of polynomials over the reals are monogenic, meaning there is a generator. Okay? And just to make it unique, you take it as being monic, and this is the Sato-Bernstein polynomial. Okay? So the Sato-Bernstein polynomial is the smallest degree monic polynomial for which you can realize a relation like that, and we do need to understand the relevance of this relation in order to get the volume estimates you're looking for, in order to get the metric Openline conjecture you're looking for. Okay? So let's see some examples first. It's not as abstract. In fact, for any given homogeneous form, you can always compute the Sato-Bernstein polynomial algorithmically. So for instance, if you take one of the simplest polynomials as being the square of the Euclidean norm, the differential operator can be taken as the Laplacian, and in this case, you get that the Sato-Bernstein polynomial is equal to, I mean, by comparing the degree, you can see that it can only be equal to that, provided that you normalize so that it becomes monic. A much more interesting example for us is the case where f is a monomial. Again, in the case that f is a monomial, you can take the differential operator as being this one, apply to f to the s plus 1. Up to a constant of normalization, by comparing the degrees, you can see that it can only be, the Sato-Bernstein polynomial can only be this one. So what I'm saying here, and that's the piece of information to keep in mind, in the case of a monomial, we are able to completely determine the Sato-Bernstein polynomial and to get all its possible roots. Okay? So that's the Sato-Bernstein theory, but let's not forget the reason why we want to compute this, to get this volume estimate. And when we get this volume estimate, from the Borel-Cantelli lemma, we get the metric Oppenheim conjecture. Okay? And so the question is, how do we get a volume estimate like that from the definition of the Sato-Bernstein polynomial, which defines this weird formula that we need to understand the relevance of. Okay? And so I'm going to sketch the proof of this result in 3 steps. Step number 1, if you want to get a volume estimate, it's always extremely relevant to introduce a purely analytical tool, which is the Zeta distribution associated to your homogeneous form. So Zeta distribution means that if you want to evaluate your distribution at a point, you need to evaluate it against a smooth test function, so a smooth compactly supported function, and it is given by the integral of this quantity. Clearly, there is no problem of definition as long as the exponent s is non-negative. Okay, everything is well defined, everything is compactly supported, there's no problem at all. And here's the main point of the Sato-Bernstein identity, which is up there. It enables you to extend this Zeta distribution meromorphically to the entire complex plane C, meaning for any value of s. Initially, this quantity here is only defined when s, the exponent, is non-negative, and the Sato-Bernstein identity enables you to get a function, well, a distribution, which is defined over the entire complex plane. So how does it work? Well, we just multiply the identity which is here by b, and by the definition of the above identity, we get it's equal to the differential operator applied to f to the s plus 1. Okay? But clearly, this thing, let me remind you that the differential operator is a polynomial, in particular the partial derivatives. Whenever the partial derivative acts on f to the s plus 1, you can integrate by part to transfer the action of the derivation to psi. Okay? So if you integrate by part, that's just integration by part, you define what is called the Joule operator, which transfers the action of the derivation on f to the other quantities in your integral. Again, that's just integration by part. Okay? But that's really good news, because we know that our distribution is well defined when we test against any smooth test functions, and that's certainly smooth test if you apply the Joule operator to psi, as long as the exponent is non-negative. So previously when s was non-negative, and so now everything now becomes well defined when s plus 1 is non-negative. So when s is bigger than minus 1. Initially everything was well defined up to s non-negative. Now everything becomes well defined s bigger than minus 1, and so you can certainly keep on going in order to get the extension to the entire complex plane. Okay? And the additional piece of information that you get is that there's a problem in order to recover the value of your distribution when you cannot divide by bf. In other words, and that's the reason why this volume estimate is expressed as a function of bf, the poles of your meromorphic extension are contained in the roots of your Sato-Bernstein polynomial. Okay? So that's really, so like I said, this Sato-Bernstein theory is extremely useful also in quantum field theory and in other areas. In mathematics, actually, one of the reasons why it was, actually that's a question that was asked in the ICM in '56, can we extend meromorphically this Zeta distribution? And that's the reason why Sato and Bernstein worked on it in order to define this identity, which precisely enables you to do precisely this. Okay? So let's not get carried away. We want to compute some volume estimates, and we introduce some zeta distribution. What's the point? Well, in complex analysis, it is well known that if you want to see how your domain grows like a volume like that, well, clearly, the poles of your zeta function should tell you something about the way your function f vanishes around its zero set. Okay? The way it blows to infinity depends on how small f can get around its zero set. So the natural way in complex analysis to formalize this intuition is to use what is called the talbarian theorem, so a well-established topic, which tells you that, well, in fact, I've got a volume estimate which is here. In fact, it is true, and it is well known to be true, if instead of working with the Sato-Bernstein quantities like the roots and the multiplicity, you do exactly the same with the zeta distribution. Okay? So we do have the volume estimate which is up there. If you work with the poles, the largest pole of the zeta distribution, and the corresponding order, instead of working with these Sato-Bernstein quantities. So again, that's a talbarian theorem in complex analysis, not a very difficult one, by the way, but that's exactly what it does, actually. Okay? And so, of course, the only thing that is left for us is to show that the order and the multiplicity, the largest pole of the zeta distribution coincides with the root that we're considering of the Sato-Bernstein polynomial, and that the order and multiplicities are the same, so that we get precisely this volume estimate with the Sato-Bernstein information. Okay? And the way we're going to do that, that's the final step in the proof, is to do this by resolution of singularities. So I don't expect necessarily everyone to be familiar with this, but again, it's not as scary as it looks like. Resolution of singularities just tells you that provided that you work with nice enough functions, so analytic functions, and homogeneous polynomials are necessarily analytic, if something bad happens, it cannot be too bad. Okay? So what does it mean that something bad happens? It means that you're around a zero set, a point where f vanishes, so something like this, or something like this. But at the same time, you do not know where to orientate around this 0 point, because the gradient also vanishes. So you're somewhere here or somewhere here. Well, a resolution of singularities tells you that, well, if you're in a bad situation like that, it cannot be too bad, because upon making a change of variables, you can bring the problem back to the simplest problematic case that you understand really well, the case of a monomial. Okay? So a resolution of singularities tells you that working in a suitable neighborhood of your problematic point, you can get the simplest possible form of singularities, so where a phenomenon like that happens, namely the case where f is a monomial. And that's really good news for us, because the example that we saw before is that, well, we know how to compute the Sato-Bernstein polynomial of a monomial, and as you can guess, we should be, and we can indeed, compute all the poles and multiplicities and orders of the zeta function associated to a monomial. It's just a basic calculation. So you just need to compute the two quantities that you're able to compute really well to see that they match in order to prove exactly the identity which is up there to get the volume estimate. Okay? So really it's a mix between analysis and algebra in order to get this kind of volume estimates. But let's not get carried away. The reason why we wanted to get these volume estimates is because we wanted to prove this metric generalization of the Openline conjecture. That was really the missing piece, and we have it. So what do we get as a consequence? We wanted to compute the size of the smallest solution to our homogeneous form inequalities in a generic sense. We needed the volume estimate, which is just what we've got. And so as a consequence, we can get a precise answer for the problem. Here it is. If the minimum function behaves not abruptly, that's really the meaning of this limb subcondition, which is really a very mild condition. If you're in the non-trivial case where you assume this, that's really the meaning of this second condition, so you're dismissing any trivialities, well, you can get that the minimum in a generic sense is less than your function h, provided that a certain volume sum, depending, well, precisely on what you're able to compute, converges. Okay? So I'm not sure it's any more eliminating, but if you want a precise example, if you take a power, you can take the power as being bigger than a certain quantity, which is explicit. Okay? So we do get precisely a quantitative version of for the smallest solution of our inequalities by these volume estimates. And the second question that we said we would be able to solve is to count the number of solutions from the Borel-Kant lemma, provided that we are able to get the volume estimates, which is precisely what we're able to do. Okay? So we should now be able to also compute the generic behavior of this counting function thanks to this new input. And so what does it give? Here's the answer. You can realize the heuristic that we were looking for, namely that the number of solutions grows like the volume of your domain. The main input is that you're able to compute the volume now with an additional restriction, this thing here. So this condition means that the growth of your domain has to be at least polynomial because you do not want the root to take its maximal value n over t. So provided there is enough expansion in your set, at least polynomially, you do get precisely the heuristic that you're looking for. The number of integer solutions to your inequality is asymptotically equal to the volume of the set of real solutions. Okay? And so what we get here is precisely that we wanted to get a metric Openline conjecture. We reduced it to the problem of homogeneous forms. And now that we understood the way that these homogeneous forms and inequalities work, well, we can get back to the Openline conjecture. What we're going to do now is to work out with the second problem, the problem of approximation of polynomial curves, which seems to be seemingly completely unrelated. But what we will see is that it precisely comes down to understanding the very same semi-algebraic set that we computed the volume of. Okay? So again, seemingly these two problems are unrelated, but here is the reason why they are related. So here is the problem. What is the hardware dimension of the set of real numbers which are well approximated at a given rate, 1 over q tau, simultaneously with a cube? The problem in full generality is open. Or of course, there's nothing about working with a cube. What is the other dimension of the set of real numbers which are well approximated at a given rate, simultaneously with a polynomial value that they take? The problem is wide open in full generality. Okay? So I should say that I will not give a full answer to the question, not only because it's very hard, but also because it's a work in progress. I will tell you how you can reduce this kind of problems to what we've discussed so far. So let's try and see what we can do, what we understand about this problem. So Arina yesterday talked about Dirichlet's theorem. So if you apply Dirichlet's theorem in dimension 2, well, clearly the pigeonhole principle tells you that you can always simultaneously approximate x and y up to an exponent 3 over 2. So basically, as long as tau is less than 3 over 2, you get full dimension. So you just take y to be equal to p of x. That's really the pigeonhole principle. Can you go beyond the Dirichlet bound and the Dirichlet exponent 3 over 2? Well, yes, but that's already extremely hard work. That's a result due to Bereznevich, Dickinson, and Vellani, which tell you that if you work between 3/2 and 2, so you go beyond the Dirichlet exponent 3/2, provided there are some curvature conditions which are satisfied, and in our case they're trivially satisfied because we're considering polynomials of degree at least 3, meaning that the second derivative has only a finite number of zeros, then you can go beyond and compute explicitly the value of the Hausdorff dimension. Okay? And so this thing is really harmonic analysis and really Fourier analysis. And so as a consequence, you can win a bit more over the Dirichlet exponent to say that you can go up to the exponent tau equal to 2. Big question, what happens next? And this thing is really hard. Okay? So let's try and analyze the problem to see why it comes down to understanding the properties of the semi-algebraic set that we've been working with. I'm not going to do any magical trick of most simple thing. I'm just going to apply Taylor expansion. Okay, so let me assume that, again, I can work over a compact exhaustion of my space. And let me assume that I'm working with x in a bounded domain, and with that loss of generality, I'm looking for the solutions with a bounded denominator. So with that loss of generality in a dyadic range, capital Q and capital Q over 2. No big trick, I'm just going to apply a Taylor expansion. The value of the polynomial P over Q, I'm going to Taylor expand it at the value of x. And so what I do get is that, well, the R term will always contain the gap between x and P over Q, which I know by assumption to be 1 over Q tau. So I get a big O of 1 over Q tau here. P over x, by definition, is within 1 over Q tau of R over Q, so I get R over Q plus the R term, which is 1 over Q tau. That's basically it for the analysis, because what I'm going to say now is just to say that I take this equality, this equation that I've got here, and I'm going to multiply by, let's say, Q to the D. The point for me is to work with integers. So what I do get, Q to the D times the polynomial evaluated at the rational minus R times Q to the D minus 1 becomes less than the right-hand side, which is the size of the denominator, to the power of D minus tau. So again, it's just a Taylor expansion when I clear off the denominator in order to work with integers. So if we just summarize what we did, we want to compute the Hausdorff dimension of this set. We're down to computing, that's the first step of the analysis, the number of solutions to a homogeneous form inequality. And here is what happens. We get exactly the same semi-algebraic set that we wanted to compute the volume of, except that now we need to work a lot harder in order to find the number of lattice points, the number of integer vectors falling in this set. Okay? So the problem now becomes much more difficult. It's not only about computing the volume of this semi-algebraic set, it's about counting the number of integer solutions, and that's just the first step in order to solve the Hausdorff dimension result that we're looking for. Okay? And so here again, we're going to make a kind of a mix between analysis and algebra. And so just to say that we've reduced the problem of approximation of Filmmaker to this same problem of understanding homogeneous form inequalities. So if I want to summarize the goal, we consider the same algebraic set, and we consider the very same dependency between B and A without loss of generality. And we want to compute the number of solutions, of integer solutions falling in our set as well t as the parameters tend to infinity. Okay? So here, in the same way as before, we mixed up distribution theory with some Sato Bernstein algebraic theory. We're going to mix up some analysis with another kind of algebraic theory. And so the analysis here is pretty simple, almost straightforward. I want to count the number of integer solutions of this. Well, I'm just going to write it as the sum of the characteristic functions when I evaluate at the integer point. So this thing here means that the integer vector k lies in a ball of radius, 1 dilated by t, so the ball of radius t. And this is the characteristic function of the interval 0, 1. Well, when writing something like this, I really didn't do much. Nothing really happened. Just another way to rephrase the same counting problem. But the main difficulty with this is that the characteristic functions are extremely discontinuous. Okay, they're not continuous. So there is nothing I can do if I just write things like that. What I can do, though, is to approximate my characteristic function in the most classical way by, well, smooth, compactly supported function which bound them from above. Okay, so this thing here will be bounded above by, well, functions which approximate well the characteristic functions, but in a smooth, compact way. And what is the point of doing that? Well, you've got this wonderful thing which is called the Poisson summation formula, which tells you that provided that you work with nice enough, regular enough functions, the sum of the values they take at integer lattice points is equal to the sum that their Fourier transform takes at the same integer lattice points. In other words, the Poisson summation formula precisely tells you that this quantity here is the same as the quantities when you sum over the Fourier coefficients, which Fourier coefficients, of course, we can explicitly write down. Okay? So it's a most classical way to count lattice points problems. And let's just try and see what we can get from this expression of the Fourier coefficient. Clearly, when y is equal to 0, I'm integrating psi and psi, where psi approximates the characteristic function of the ball and psi the characteristic function of 0, 1. So basically, when y is equal to 0, I'm just getting the volume of my algebraic domain. Okay? So that's because there is no exponential term. The other thing we can note is that if we just integrate by part, so this exponential up and everything else down, so we differentiate. As the norm of y tends to infinity, this Fourier coefficient will tend to 0. That's the most classical phenomenon, but we get an extremely fast decay because we can integrate by part as many times as we wish, because our function psi and xi are smooth, so infinitely differentiable. Okay, so just two pieces of information. At 0, we get roughly the volume of our domain, and as y tends to infinity, we get an extremely fast decay of our Fourier coefficients. So if we put these two things together, what we get is that we're going to fix a free parameter m. I'm going to write the Poisson summation formula. And according to what I just said, we're going to split the sum into three pieces. The zeroth term, which is the volume, a middle range that we need to understand, and a large region where there's fast decay. Okay, so like I said, when we've got at 0, we've got the volume of our set, which we were precisely able to compute. It's supposed to be the main term. When we are at large value, provided the m is large enough, this thing by integration by parts, using integration by parts is basically the only analytical tool that you're using in this talk, you get everything that you want from that. So by integration by part, this thing, when m is large, has extremely fast decay, so we understand very well. So everything here is about understanding the middle range, which will determine the error term in our counting estimate. Okay? And so if we do that, we get that the number of lattice points that we want to count is the volume of our domain plus a middle range of Fourier coefficients that we need to understand. We need to see, upon adjusting all the parameters, how this Fourier coefficient behaves. And this is where I'm going to use something pretty surprising, a picture of a tomography. So when you go to a doctor, so when you go and see a doctor and when he wants to take a scan of your body, the way it works is that, well, he's going to send beams in all possible directions. And what is going to be of interest for him is, well, the ratio between the intensity of the beam at the entrance of your body and at the exit. If you know the ratio, then you know the rate of absorption. It tells you many things. For instance, the rate of absorption, but also the length of the distance that your beam has traveled, well, within your body. So he's going to do that in all possible directions. And the principle of tomography is just telling you that if you know the length of the sections by lower dimensional subspaces in all possible directions, then you can reconstruct your image in 3D. Well, I mean, there are experts in this room who know much better than me about this quantity, but that's exactly the principle we're going to apply. So, again, the idea, provided that we know the sections are a semi-algebraic domain in all possible directions and at all possible heights, we will know everything about the decay rate of the Fourier coefficient. Okay? How do we formalize something like that? Well, it's almost slightly disappointing. You just make a change of variables. Okay? So you decompose your k in polar coordinates, fair enough. You take your integral, and you're going to take, for one of your variables of integration, the height of your section in a given direction v. Okay? So it's almost disappointing, but what you get at the end of the day is what is called, well, if you apply Fubini's theorem, it will tell you that the n-dimensional Fourier coefficient you're looking for is equal to a single variable Fourier coefficient, and you group, by Fubini's theorem, all the integration variables u1 up to un minus 1 into a single function that you call the Gelfand-Leray form. Okay? So why is it called a form? Because, well, you know that if you want to make a change of variable like this, you need the Jacobian not to vanish. But there's no reason why you should take the last variable as the height sigma. You can take it in any other position to make sure that the Jacobian doesn't vanish. And the way to properly formalize that is to work with differential forms, and that's the reason why this is called the Gelfand-Leray form. Okay? So what does it look like? And you should say that if you make the computation, you will see that the actual quantity which depends is, again, determined by this condition, the ratio between bt and t to the t. Okay, so here's my semi-algebraic set, which I tried to make it a bit nice. And so, like I said, if we want to get the decay rate of this Fourier coefficient, we're going to disfigure it and score it by taking volumes of sections in all possible directions and at all possible heights. So from something beautiful as that, you get something as ugly as that. But the point for us is to know the volume of the length of the sections in all possible directions. And if we do that, then we're able to determine the decay rate of our Fourier coefficients, and therefore the counting estimates for the lattice points theorem we're looking for, and therefore something about the Hausdorff dimension of the set that we're looking for. I just want to remind that we just started from a polynomial as x equal to x cubed, and we still need to do something, all these, in order to get some understanding of this very simplest case that we don't understand. Okay? And so, of course, what is going on here is that you need to understand the behavior of this Gelfand-Leray form, what it does, how it behaves. And so you do some analysis. So in all cases, actually, you can get all the results that you want by just writing down explicitly what this Gelfand-Leray form looks like and trying to figure out all the properties that you're looking for. The problem, if you do something like that, is that you will get all the possible results you're looking for, but all pointwise for a single direction v. In all the analyses that you need to do in order to make sure that your estimates are correct, you need some uniformity claims. And the best way when you do so, working with semi-algebraic quantities, I mean, let's say the worst thing you can do when working with semi-algebraic quantities is to work with analytical tools. There's a theory, which I'm not going to talk about, but I'm just going to give the conclusions of this theory, which is called the theory of all minimality, which enables you to formalize everything that you want by working in an algebraic setup in order to recover with uniformity all the analytic claims. And so here is, for instance, an analytic claim that you can easily check by a single example. If you want to take the slices in the vertical direction, it's clear that you're starting from 0, you're increasing up to there, then decreasing, increasing, decreasing, and so forth. So there are only a finite number of intervals of monotonicity for a given direction. The theory of all minimality tells you that the number of intervals of monotonicity is actually uniformly bounded no matter what the direction is. So for instance, no matter what the direction is, you will never change variations more than, I don't know, 50 times or 100 times, uniformly in V. Okay? So again, checking that for a single V is extremely easy. You just write down what the Gelfand-Leray form is about, just doing some analysis, and you get it. But to get uniformity, it's much more complicated. Okay? And so, for instance, here is what your function looks like. So it increases, then decreases, increasing, decreases. Of course, there's no reason why it should be linear, but it was much easier to me to draw the picture with linearity. And so the question is, why is it so interesting that it should be monotonic? I mean, when you want to compute the decay rate of a Fourier coefficient, that's pretty much the best thing you can expect. Okay? The reason for this, if you integrate by part, there you go, once again, that's the only thing I'm using in analysis. If you integrate by part and use the triangle inequality, you will get the integral of the absolute value of the derivative. Okay? But this thing, because it keeps a constant sign, is equal to that. And this, of course, is easily computable. Okay? So this thing is telling you that the decay rate of your Fourier coefficient is governed by the maximal value that your Gelfand-Leray form takes at finitely many endpoints of intervals of monotonicity. In other words, the decay rate of your the Fourier coefficient is entirely determined by the maximal value that your Gelfand-Leray form takes at all the maximal value of the intervals of monotonicity. Okay? And so, what can we say about the way that this maximum behaves? Well, here again, if you do some analysis by just working with some derivatives and things like that, you can easily prove all the claims for a fixed value of V. If you want to get a much finer analysis, again, you need to do some what is called all minimality to confirm your intuition that you got by just differentiating in the basic setup. And what you get is that the maximal value of all possible sections at all possible height of your semi-algebraic domain, as epsilon tends to 0, so as you get closer and closer to your zero variety f equal to 0, behaves something like that. Okay? So everything here, the decay rate of the Fourier coefficient you're looking for here, is entirely governed by the behavior of this quantity. And of course, the leading term here will be this epsilon to the alpha f. And this alpha s is what we decided to call the semi-algebraic level of flatness. So again, it measures the longest time that a section spends in a neighborhood of your varieties of your semi-algebraic set. Okay? So let's put everything together. We wanted to get a problem of definite approximation. It comes down to counting a lattice point problem. We use the Poisson summation formula and these geometric tomography techniques. With some additional all minimality, we're able to show that everything depends on the maximal values of the sections over your semi-algebraic domain. which are able to compute. So putting all this together, we would just need to adjust all the parameters in order to get an answer to our problem. Okay? Well, in doing so, before getting back to the Hausdorff dimension business, here is what this thing actually does when you adjust all the parameters. So you count the lattice points. As we said, it's bounded by the zeroth term, which is the volume we're able to compute it. And the error term that we know is determined now by, well, this semi-algebraic level of flatness, which again gives the maximal value of the Gelfand-Leray form. Okay? Here is what you can do before getting into the Hausdorff dimension business. You can answer a problem which was raised by Sarnak some 25 years ago, which tells you that, well, if your zero set is sufficiently curved, so again, curvature here is the enemy because one of the sections, if it's not curved enough, it's going to spend a lot of time in your semi-algebraic domain. Well, then the lattice point counting function should be bounded above by the zeroth term, the volume, that now we're able to compute, and provided sufficiently curved, and it does not define properly what it is, but so part of the question is to make sense of this. You can get a power saving by delta compared with the trivial bound n minus 1. Okay? And so if we adjust all the parameters in all what you did, we just define the concept of curvature, you precisely get an answer to this question. Provided the semi-algebraic level of flatness is big enough compared to the growth exponent of your volume, then it is true. And in fact, the result that we prove is much more general. You've got an explicit value for delta, and it also works for a system of homogeneous forms. Okay? So let's get back now. Let's not forget that what we wanted in the first place was to compute the Hausdorff dimension of our business. So we've reduced now the problem of homogeneous inequalities to understanding the same properties, the properties of the same semi-algebraic set to the problem of approximation of polynomial curves. And let me remind you that the big question that we had is, what can we do beyond the exponent tau equal to 2? So like I said before, I'm not going to answer fully the question, but here is really what we should expect. So we're able to get a lattice point counting problem, so that's the first step as we saw from the Taylor expansion analysis of our problem with the power saving error term. If you want to work with polynomial curves, well, it turns out that you take the parameters which are n equal to 3, so n equal to 3 is the projective version of the curve, and the bt, that's what I call actually q to the d minus tau, now it becomes t to the d minus tau. Again, for Hausdorff dimension considerations, you can always work over domains where the second derivative doesn't vanish. There are only finitely many points, so you take a compactization of your space where the second derivative doesn't vanish. In this case, you can show that the volume growth is always given by this exponent, and the power saving is really good, delta bigger than 1. And so here is the expectation that you get. So you've got the Dirichlet bound when the exponent is less than 3/2. You've got the Bereznevich-Dickinson-Villani bound when you're between 3/2 and 2. You should expect that, so the Hausdorff dimension is given by which of these two terms dominates in the counting problem. When you're still less than 1 plus delta, it should still be the volume bound, and you still get the Dickinson-Bereznevich-Villani result because of the choice of parameter r equal to 1. However, when you're really with tau big, so very good approximation, then because delta is bigger than 1, you get that this term here dominates, and this thing should be an upper bound for your counting function. And provided that you adjust delta well enough, it should actually be an equality. Okay? So that's really the expectation. I mean, making that work requires some technicalities. Basically, I don't have time to do, but that's really the answer that you should expect for this problem. And so thank you for your attention.